chapter 3 and 4, which are pressure and wind. Altitude and density come right out of pressure, so we're not going to. We'll work those into this conversation. So what is pressure? There's a lot of molecules above you in the atmosphere. So all those molecules have a mass which has a weight. So what happens is, in this case, it's a barometer with mercury. We tend to not use mercury barometers anymore because mercury has been proven to be kind of dangerous. But think about it. If you have a tube that has no air, so you filled it all the way up with mercury, then you had mercury all around it down in the bottom in a little glass container. You push that tube down in the glass container, the mercury is going to come down a little ways, and then it's going to stop coming down. There's going to be some level at which it stops, a height. That height we used to measure as the inches of mercury. It is a pressure. That height changes depending on the day, depending on weather conditions. But that change can be very, very valuable in determining what the weather is going to do. So let's go through here a minute. I wanted to show you station pressure. This is a really good example, I think. When you get air pressure, if you're up on top of a mountain or higher up, the pressure is going to be lower because there's less air above you. Further down, there's going to be more pressure because there's more air above you. So we want to take that out of the equation. We want to have everything seem like it's at sea level. So if you look at observations, you're going to see a station pressure, which is what you would use if you're looking at it for your altimeter. But then you're going to see sea level pressure. Sea level pressure is where you're taking basically the standard atmosphere, using it and temperature to adjust the pressure at that elevation, wherever that station is. In this case, we're saying Denver, Colorado, to look like sea level. So that adjustment allows us to take out the height of where that station is. So we now have everything at sea level, and we can create surface weather maps, which you've seen a lot of and are going to see more of. So here you can see a standard surface weather map. We're going to get into atmospheric circulations eventually. Notice high pressure along one latitude, another one here, low pressure along a different latitude. There's a reason for that. And we're going to talk about that reason eventually. So we have constant pressure charts and all of that. One of the things I want you to notice is the atmosphere goes up and down, literally like a wave in a way. And with that, there are different pressure charts. And I wanted to show you here, for example, here is an 850 millibar chart. The lines on it are contours, the height above the ground. So the lower the height, it literally corresponds to less atmosphere above it. It gets lower pressure. So here would be low pressure, literally up over Hudson Bay. Pretty intense for this time of year, actually. Higher pressure off the southeast coast down in here a little bit. So the circulations around them are similar. We could go back on this chart, and I could look at, let's look at 500 millibars maybe today. Well, 500 millibars is going to show contours again, but a little higher up in the atmosphere. Basically about halfway through the atmosphere. And again, these are contours, so lower pressure is up here, Higher pressure is down in this area. So that is what I want you to get out of pressure. And with that, we're going to move on to the altimeter and all that. You have those on your planes. I'm sure they're a lot more sophisticated than what this gentleman has put in the book. But with that, we have a standard atmosphere. Everything is based off of a standard atmosphere. Well, the atmosphere is very rarely standard. So if the pressure that you are inputting is wrong, then you're going to be either high or low. If you have when the altimeter is set to different pressures. But if the standard atmosphere is wrong, say it's warmer than normal, well, then your height is going to be higher. And if it's colder than normal, you're going to be a little below that height. So I wanted you to understand that a little bit. So the atmosphere is less dense. We know that when it's warmer. So that means that instead of pressure decreasing at what would we consider the standard rate, it's going to decrease at a different rate, slower. If the atmosphere is colder, the molecules are packed closer together, the atmosphere is going to decrease pressure at a faster rate. So when we were looking at these pressure charts here, I looked at temperatures. The coldest temperatures are up here where the lowest pressure is. So the pressure decreased faster where the temperatures are colder, where the air mass is colder. It's a real quick way to look and say, oh, the pressures are lower up above me at 500 millibars. I got a colder air mass below that area. So if I'm flying into there, I can expect pressures to drop at a faster rate than would be the standard atmosphere. I might be flying lower. I'm sure there's other methods now you all use, but that would just be if you had very rudimentary understanding of things. So that is the altitude and pressures. Now let's go into winds. All right, I've got a quick slide presentation here. Back here a minute. So, winds, where do they come from? Why does that air move? Well, something has to push the air. Like when you move your car or when you move yourself, you're pushing yourself. You're exerting a force. That force is what moves air. Force is very simple. It's mass. So mass is, how many molecules are in this little area? That is mass. Acceleration is how quickly you get those molecules moving in one direction. So the two combine to move the air. So there are certain factors that go into this. One of them is pressure gradient. All right, if the pressure is gradient is very tight, the atmosphere hates that. So what it's going to do is try to get rid of that pressure gradient. So if I had a big pile of heavy marbles in one area, and then next to that I had almost nothing, those marbles are going to want to tend to come down, fill in the bottom gap, make everything level. So the closer, the steeper that slope is, the quicker those marbles might move. Same holds with air. Air is going to blow from high pressure to low pressure, always. And the tighter that gradient is, the quicker that air is going to move from one to the other. That's why in a hurricane, the air pressure gradient is extremely tight. So the air is going to want to move from that high pressure to that very, very intense low pressure very quickly. That's why the winds are so strong. So with that, let's go on to the next one here. There's another force called centripetal force. It's a curved force. When you go around a curve in your car, what keeps you on that curve? what it is, just like the rope holding this ball, it's centripetal force. I watched these people perform at the Olympics and was just amazed. They could spin these things around so fast and throw them so far. So that is what centripetal force is. So another force, it's a little more fun. Coriolis force. We have a rotating Earth. The Earth, instead of, not rotating at all, it rotates. So you think about it. In one day, one place on Earth is going to go all the way around. Well, if I'm at the equator, I'm going a lot further than if I'm at the, say, up in Hudson Bay, where the Earth isn't quite as far around as down in the equator. So that means that generates a force on wind called the Coriolis effect. So in the northern hemisphere, because of that, any wind is pushed to the right. And the Coriolis force is stronger towards the poles than it is on the equator. Matter of fact, it goes to 0 on the equator. So if I was shooting a billiard ball and I was up at the near the North Pole, I'm going to have that ball deflect much more than if I was down at the equator where it's not deflecting at all. That little bit of difference might make your shot work or make it miss. So, believe it or not, the best billiards players actually take this into account, depending on where they are in the world. So, keeping moving along. Also, something called gravity. Yeah, gravity pulls the air down. It's what keeps that air from pushing out and going out. Because it affected the centripetal force of the Earth rotating. So, with that, why the heck atmosphere? There's a heck of a pressure gradient. You just saw me put up a couple of charts here for 150 millibars and 500 millibars and 850 millibars. The pressure gradient is very strong. So why don't all the atmosphere, all these air molecules just go flying upwards? After all, we want to get rid of low pressure, right? Lower pressure is above us. That is all because of gravity. We have what we call the hydrostatic balance. The force of gravity equals the pressure gradient in the vertical. When they match, we have a hydrostatic balance, and that is what keeps our atmosphere where it is. There are a few types of wind. I'm just going to touch these quickly, but there's a geostrophic wind. Geostrophic winds flow when the air flows parallel to an isobar or a contour. What happens is there's a balance between the pressure gradient force and the Coriolis effect. There's only two forces involved, pressure gradient and Coriolis, and they cause the air to blow straight in a nice straight line parallel to the isobars or contours. Now, let's add in another one. Around high pressure or low pressure, the air flows in a circle. So now we have unbalanced force, and we wind up with centripetal force in here. That is what changes the flow to a circular pattern. Finally, when we get down to ground, we have friction. There's not a lot of friction up in the atmosphere, the higher up you get. There's some turbulence caused by friction, which there is some friction up in the atmosphere. I'm not going to say there's none, but there's more friction the closer to the ground. And there's more friction the rougher the ground is. So in other words, mountains, hilly terrain, a lot more friction, a lot more force caused by friction than if you were flying over water, which has very little friction. So, as the air moves across this area, if you're down near the ground, what happens? Friction slows the wind. It pushes the pressure back on, tells it to slow down a minute. If it slows down, it means the Coriolis force isn't as strong. So instead of moving, nice and parallel to these contours and millibars here, pressure isobars, what we wind up with is the actual wind blows towards low pressure some. So instead of being nice and moving right along with the isobars, it actually moves towards low and away from high pressure. So there you have the wind. So that's what I wanted you to get out of all of this. I hope you have a little basic understanding of all this. And yes, there's a lot of questions in the lab about using winds or using pressure. And all of that relates to what you just learned. And you're going to talk about METARs and all of that. Many of you know METARs already. If you don't, well, here's your chance to learn. If you have any questions about it, please don't hesitate to ask.